Hello and welcome everyone to our weekly session titled Latest in Bitcoin Tech. And this week we will go through the Bitcoin Optech newsletter number 330, published on November 22nd, 2024. So we'll probably have a shorter session this week. We will cover the changes to services in client software in probably 2 or 3 PRs. Uh, so let's look at the first one in the section of changes to services in client software. Spark Layer 2 protocol announced. Spark is an off-chain, state chain-like protocol that supports the Lightning Network. Let us first understand what state chain is. Okay, so the first uh, bullet point in the changes to services in client software is pertaining Spark. What is Spark? It is an off-chain, state chain-like protocol that supports the Lightning Network. So basically, it's a layer 2 protocol. State chains, what are state chains? State chains are a proposed off-chain system for allowing a user, such as Alice, to delegate the ability to spend a UTXO to another user, that is Bob, who can then further delegate the spending authority to a third user, Carol, etc. So the conventional way of spending a UTXO is that there is a person who possesses the private key that is required to spend that UTXO. And once he spends that UTXO, he loses possession of that UTXO, and the possession of that UTXO is transferred to the recipient. So if Alice wants to spend a UTXO, Alice is the sender and Bob is the recipient. Once Alice sends that UTXO to Bob, and that UTXO comes to the possession of Bob. Bob is now the new owner of that UTXO, right? But for that to happen, the UTXO needs to be spent on chain. Like this entire transaction needs to be embedded on the blockchain, and the ownership needs to transfer hands. Okay. What state chains do is state chains are a proposed off-chain system for allowing a user such as Alice to delegate the ability to spend a UTXO to another user, Bob, who can then further delegate the spending authority to a third user, Carol, etc. So you don't have to make actual payments on the mainnet. You don't have to embed this information on the blockchain. You don't have to actually mine the transaction. Off chain, you can transfer the ownership of a UTXO from one person to the other person. So if Alice owns a UTXO, she can transfer the ownership. She can delegate the ability to spend the UTXO to another user, that is Bob, and who can further delegate the spending authority to a third user, that is Carol. The off-chain delegation operations are all performed using signature adapters and the cooperation of a trusted third party who uses L2 mechanism and their knowledge of every previous delegation operation to ensure each new delegation uses a state number higher than any previously used state number. These incrementing state numbers ensure an on-chain spend by the most recent delegate, that is Carol, can take precedence over spends by previous delegates, Alice and Bob, assuming the trusted third party hasn't colluded with a previous delegate to cheat. So this is pretty similar to how we have like how states of a Lightning network are changed, right? We keep a track of the recent state. Every time a transaction is made on the Lightning network, uh, we keep a track of the change in the state. And when the commitment transaction is broadcasted to the mainnet, this keeping track of states ensures that the final state is the one that is confirmed on the blockchain. And if anybody tries to broadcast a revoked commitment transaction, then they get penalized, right? So the same mechanism is carried forward in state chains, not entirely, but only the states, meaning that every single time the ownership of a UTXO is transferred from one person to the other, the ability to spend a UTXO is delegated from one person to the other. That is deemed as a change in state, meaning change in ownership. And the state can change as many times as you want off chain. And eventually, when you broadcast that transaction on the main net, it is the final state. It is the final state that will be recognized. Beyond colluding with a delegated signer such as previous delegates Alice or Bob, there is no way for the trusted third party to steal funds. A delegated signer can always spend the UTXO on chain without needing permission from the trusted third party, arguably making state chains less trusted than federated side chains. So there's a third party involved. There's a third trusted entity involved that cooperates in transferring states or in delegating the ownership of UTXO from person A to person B. However, the existing owner of the UTXO can opt out off chain, can opt out of being off chain and go on chain without requiring the consent of the trusted third party, making state chains less trusted than federated side chains. Although initially described for use with Schnorr-based signature adapters, there has been work to adapt the protocol to ECDSA-based multi-signatures and to use decrementing block times similar to that proposed for duplex micropayment channels rather than L2. This would make state changes. This would make state chains usable on Bitcoin without depending on any proposed consensus change. We'll read this once again. Although initially described for use with Schnorr-based signature adapters, there has been work to adapt the protocol to ECDSA-based multi-signatures and use decrementing lock time similar to that proposed for duplex micropayment channels rather than L2. This would make state chains usable on Bitcoin without depending on any proposed consensus changes. We know what ECDSA-based multi-signatures are, and we also know what duplex micropayments are. We covered them recently. Let's just go through them briefly and then we'll summarize. Okay, this is an entire article. Sorry, you can go through it. So basically, decrementing lock times are like, when you are routing a payment on layer 2 via multiple hops, each hop has a decrementing lock time as compared to the next one. Each hop has a decrementing lock time as compared to the next one. So what are state chains basically? State chains are off-chain or layer 2 protocols where it is possible for the ownership of a UTXO to be delegated from person A to person B without going off-chain via collaborating with a trusted third party. And the current or the existing owner of the UTXO, meaning as per the final state, has the option to opt out of the state chain and go on the main net, thereby making it less trusted than federated side chains. And at the same time, the delegation is done with cooperation or collaboration of this third party. So this is what state chains are. Now that we know what state chains are, let's read through what Spark is. Okay. How does it work? What do we will need here? Well, let's see how does it work. Okay, we'll not go into the technical overview. We'll just go into the high-level overview. Spark brings together several concepts introduced to the Bitcoin community over the past few years and is heavily inspired by state chains with a lot of empathy since we've gone through the same process ourselves. We'll take the time to explain each concept, making it as clear and enjoyable to read as possible. This section is still relatively high level. For the technically savvy, we invite you to read our technical review, which gets into the weeds of Spark. The general idea of Spark is that it allows assets on Bitcoin to be spent off-chain instantly. In Spark, the user sends funds into a shared signature address where the user retains full control of their funds and the ability to exit without any interaction from any other party. The participants of this address are the user and the operators of Spark. When a user wants to transfer ownership of these funds, the Spark operators adjust their keys so the new owner takes control, while the overall signature key remains static. The beauty of this is that at every moment, the current owner remains in full control of their funds and can exit at any time without needing permission from anyone. While users look to SOs to validate transactions by adjusting keys to reflect those transactions, the SOs do not assume control over user funds. So basically, you send your funds to a multi-signature address, which is owned by yourself and the third trusted party. And despite that, you completely own the UTXO yourself, meaning you can exit. Uh, you can exit and opt out of this protocol and go on the mainnet without anybody else's consent. You only need collaboration from the trusted third party to delegate ownership of the UTXO from one person to the other person. There are several ways to interact with Spark. Move funds in and out of Bitcoin, move funds within Spark to other users, move funds in and out of Lightning. All right, let's just go through some key definitions. and see a few things that Spark can do before we move on to the next client. To fully understand how these transactions work, it helps to know who's doing what and how everything fits together. Okay, so these are the different entities, or these are the different elements of the protocol. One is known as Spark entity. What's that? A group of entities, individually called SOs, that help facilitate the transfer of UTXO ownership between users on Spark. Their job is simple. They generate, manage, manipulate, and delete their keys. This group can add and remove more operators via consensus to improve trust and performance. So these are basically the third party, the trusted third party that are involved in the multi-signature account where the funds are parked, and they also come into the picture while delegating ownership from person A to person B. Now, these are a group of entities, and I think the singular is known as a Spark operator. So a group of Spark operators are known as Spark entity. One of the operators within the SE, they're mainly responsible for signing transactions and enabling transfers. They collectively make up the SE. So the singular is SE, and collectively the singular is a Spark operator, and collectively they're known as Spark entity. Spark service providers, just like we have Lightning service providers, we have Spark service providers. SSPs make transfers on Bitcoin and Lightning to from Spark cheaper and more efficient. Anyone can be an SSP, though we expect these will largely be wallet providers, exchanges, market makers, etc. Some entities will likely be incentivized by charging a small fee for their services. Leaf or leaves, these are virtual representations of a UTXO within a Spark. So a UTXO is represented by a term which is known as a leaf or leaves. Moving funds into, within, and from Spark. Now that you're familiar with the key terms, we can dive into Spark and see how everything comes together. As mentioned earlier, there are a few ways to move funds in and out of Spark. So from the mainnet, how do you go to Spark? From Bitcoin to Spark. From your existing wallet, all you have to do is send some BTC to a deposit address shared by both you and the SC, as we discussed above, right? Before you transfer funds into Spark, you and the SC will sign an exit transaction. This is so that if the SC ever goes offline, you can reclaim your funds on L1 to your preferred address. Once your deposit is confirmed on chain, you're all set. Congratulations, you now have funds on Spark. All right. So you have funds on your Bitcoin wallet. You send those funds to a music address, a multi-sig address, which is controlled by yourself along with the Spark entities, and you sign an exit transaction, which gives you full control of the UTXO. So meaning you can exit the protocol and go to the mainnet whenever you wish. This is an illustration of the same. So the user is sending funds or Bitcoins to this shared multi-sig address, which is shared by the user and the SE. What is the SE? The Spark entities, which is the collection of Spark operators, I believe. Yeah, Spark operators. Spark to Spark. Now that you're on layer 2, how do you make transactions at layer 2? Because eventually that's the end goal. You can transfer ownership of a leaf to other users within Spark by coordinating with the SE. A transfer is only considered valid when the receiver holds a fully signed Bitcoin transaction they can use to unilaterally exit. Right? So to exit from layer 2 to layer 1, you can do that unilaterally, but to transfer funds from layer 2 to layer 2, meaning from one user on layer 2 to another user on layer 2, you need collaboration with the Spark entity. This is an example. User plus SE. So the Spark entity needs to sign. You cannot unilaterally delegate the ownership of a UTXO or what is referred to as a leaf from one person to the another person without the consent of the trusted third party, that here being Spark entity. Lightning to Spark. Now these are atomic swaps. You can swap from the Lightning network to Spark and from Spark to the Lightning network. Users within Spark can always send and receive payments directly via existing Lightning network rails. Importantly, Spark users don't need to run a node managing Lightning channels or lock up liquidity themselves. This eliminates almost all the overhead associated with traditional Lightning operations while providing true offline receive, which isn't available in typical Lightning. All Lightning payments are facilitated by SSPs who accept funds on Spark to send Lightning payments or receive Lightning payments in exchange for funds on Spark. These transactions are executed through atomic swaps, ensuring that neither the SSP nor the user is at risk of losing funds. From what I understand is that SSPs, they charge a fee. They charge a fee, just like LSPs charge a fee. All right, they charge a fee for providing service for atomic swaps. As a user, SSP sends BTC on Spark, receives BTC on Lightning, sends BTC on Spark, and then from Spark to Lightning. So this is an example of an atomic swap. From the mainnet, you go to Spark, and from Spark, you go to Lightning, and then Spark to Bitcoin, going back to the mainnet. Spark is designed in a way that ensures users are able to exit to Bitcoin L1 whenever they want without needing permission from anyone. There are two ways to exit Spark to L1. We've discussed this previously, that this protocol allows unilateral exit. You can go to the mainnet without requiring consent or permission from anyone. Now, there are two ways of doing that. The first is unilateral, like cooperative exit, and the other is unilateral exit. And this is similar to the Lightning Network as well. What is the cooperative exit? This is the cheapest and fastest way to exit Spark. Similar to Spark Lightning transfers, cooperative exits are executed through atomic swaps with an SSP exchanging Spark funds for on-chain Bitcoin, right? And the unilateral exit, this represents the most pessimistic scenario and can occur at any time. While there doesn't need to be a specific reason to unilaterally exit, users might choose this option if a set of Spark operators goes offline or if they've lost confidence in the Spark entity itself. Unilateral exits are most expensive than cooperative exits because more than one transaction needs to be published to prove ownership of the most recent stake. There's a lot more to cover, but we won't go into that. I think we'll give an adequate amount of time to this specific client. To summarize, the specific client is known as Spark. It is a layer 2 protocol like the Lightning Network. It is governed by the Statechain protocol, meaning it's possible for somebody to delegate the ownership of a UTXO from person A to person B without going on chain with collaborating or with collaboration with a trusted third party, which is known as a Spark entity in this case. And this allows you to send your funds from Bitcoin mainnet to layer 2, which is Spark, and it allows you to transfer funds from one Spark user to another Spark user with the consent of the Spark entity, and it allows atomic swaps, that is transferring funds from Spark to Lightning, and then it allows you to exit unilaterally back to the mainnet. And there can be two ways of exits. One could be the cooperative exit, and the other could be the unilateral exit. And we've covered both the scenarios. So yeah, that is what we had to share about Spark Layer 2 protocol. If there are any questions, please feel free to ask, interrupt. I won't stop because this session will not be a very long session. But if anybody has any questions, feel free to just unmute yourself and ask. Also, if anybody has anything to share or anything to talk about, please feel free to unmute yourself and speak. The next one being Unify wallet. Unify is a BIP78 compatible Payjoin wallet that uses Bitcoin Core and coordinates PSBTs over Noster. BIP78 is a BIP that governs Payjoin, if I'm not wrong. Let us just see. Yes, simple Payjoin protocol. So BIP71 governs Payjoin. What is Payjoin? So Payjoin is a technique for paying someone while including one of their inputs in the payment in order to enhance the privacy of the spender, the receiver, and Bitcoin users in general. The general idea is also known under the names pay to endpoint, P2EP, and bus to pay. By including inputs from both the spender and the receiver, Payjoin makes it difficult for blockchain analysis companies to determine which inputs and outputs belong to each participant. Usually in a Bitcoin transaction, what happens is that there are inputs and there are outputs. Now, these inputs are created by the spender. Usually the inputs are created by the spender, okay? And people who are experts in blockchain heuristic, people who monitor the blockchain to try and de-anonymize Bitcoin users, they have certain techniques that they can deploy to correlate transactions on Bitcoin with either their users or their use cases. What Payjoin does is that it is a technique that creates or curates transactions in a manner that both the sender and the recipient participate in creating the inputs. Okay, so if Alice wants to send some Bitcoin. Let's say if Alice wants to send one Bitcoin to Bob, usually what happens is that Alice chooses a UTXO from her wallet, an unspent UTXO, an unspent transaction output from her wallet, and she signs it and she broadcasts it to Bob's address. Uh, with Payjoin, what is done is that this stereotypical mechanism is altered such that even the recipient participates in the input, right? So what they can do is that Alice takes, for instance, one Bitcoin and Bob takes, for instance, zero point zero 0.02 Bitcoin. Now they have 1.2 Bitcoins, and the recipient might get some share of it, and the sum might go to a change address of the sender, right? So instead of the sender unilaterally creating the input, the sender and the recipient both come together to create the input of a transaction, thereby obfuscating or making it less obvious who or which UTXO exactly the sender owns, right? That is what Payjoin is. So this is a new wallet called Unify wallet. Okay, it's compatible with Payjoin. It's compatible with it's a BIP78 compatible Payjoin wallet that uses Bitcoin Core and coordinates with PSBTs over Nostr. Over Nostr. All right, I wasn't aware of that. What are PSBTs? I'm sure most of us know what PSBTs are, right? Partially signed Bitcoin transactions. All right, so whoever is interested can explore this wallet that is compatible with Payjoins or that deploys or incorporates Payjoins or and coordinates PSBTs over Nostr. All right. The third one is where do we go? Bitcoinutils.dev launches. The Bitcoinutils.dev website provides a variety of Bitcoin utilities, including script debugging as well as various encoding hash functions. What is this website, Bitcoinutils.dev? Okay, so basically this website, what it does is that it provides a bunch of utilities for developers. Okay, so you have SHA-256 here, I guess. This tool will compute the SHA-256 hash of a UTF or a hexadecimal input. So you can give a hexadecimal input, you can paste, I believe, a hexadecimal input here. What happens? Yeah, okay. So as you can see, when you paste an input over your UTF-8 string or a hexadecimal input, uh, if SHA-256 output will be computed in, and you get the output. So for some use case, if you want to compute the SHA-256 of of a UTF-8 string or a hexadecimal input, then this tool lets you do that. And there are a lot of other hash functions that you can see that are frequently used in Bitcoin, like write MD160, like what's hash 256? It's the double SHA-256 hash, right? Yeah, it's the double SHA-256 hash. So if you want to hash SHA-256 twice, that's hash 256. Then we have hash 160, which we also use in Bitcoin. What is hash 160? This tool will compute the SHA-256 plus write MD160 hash. You have SHA-1. Then you can also encode stuff. This tool will convert a hexadecimal input to its ASCII equivalent, UTF-8, BESH32, BESH32M, public key. This tool will convert a private key over to a public key, a point on the curve. I was planning to do something of this sort because we're currently doing coins. So I was planning to do something like this, like a random number generator that will generate a private key, then it converts it into the public key, then it converts it into the Bitcoin address, then it concatenates the checksum, and then it converts it into a BESH32 M output. So going all the way scratch from creating entropy to a BESH32 M usable Bitcoin address. But we now have a ready-made tool. You can just generate a random number, a random private key, and it will be converted into BESH32 and BESH32M, into public key. And then using a private key, you can create a digital signature, script decoder, script debugger. So yeah, lots of fun stuff. Nice. Especially folks who are doing programming Bitcoin cohort. This might interest you. All right, cool. Moving on to what's next. Great Restored Script Interpreter available. Great Restored Script Interpreter is an experimental interpreter for the Great Script Restoration proposal. Okay, this is a YouTube video. We will wait restoration Bitcoin. Okay, yeah. For those of you who don't know what the Great Script Restoration is, in brief, we'll just go through it. It is something proposed by. All right, let's just read a few lines of it. We'll get an overview of what this is. We won't be in need of reading the entire thing. Bitcoin was initially designed with a fully fleshed out scripting language intended to encompass and support any potential safe use case that users could come up with in the future, as Satoshi himself put it before he disappeared. The entire intent was to give users a general enough language that they could compose their own types of transactions as they saw fit. That is, give users room to design and experiment with how they program their own money. Before he disappeared, Satoshi ripped off 15 of these opcodes, disabling them entirely and adding a hard limit to how big a piece of data could be manipulated on the scripting engine stack. That is 520 bytes. This was done because he frankly screwed up and left open a large number of ways that complicated scripts could be used to denial of service attack the entire network, creating huge and costly to validate transactions that would crash nodes. So basically, there were a lot of opcodes that were a part of Bitcoin initially when Satoshi was working on Bitcoin. And before he disappeared and retired from working on Bitcoin, he disabled a lot of those opcodes. Okay, for different reasons. Some of the reasons might be known to us. He might have shared some of the reasons he might not have shared with us. The point being, there were a lot of opcodes which were active on Bitcoin, and later on they were deactivated. This is a proposal by, I can't remember his name. Is it Rusty Russell? Who is it? I don't know. Who was it? Who was it? I think the YouTube video might have the name of the author.
A great job, car, and home.
Yeah, Rusty Russell. Rusty Russell. Okay. So he is proposing that all these opcodes be activated again. Opcat, what does it do? Takes two pieces of data on the stack and adds them together to form one. Opsubstr takes the length argument in bytes and grabs a piece of data off the stack, removing that many bytes from it and putting that. Point being, these opcodes: op left and op right, op invert, op add, op or, op XOR, op shift, op downshift. All right, these were opcodes that were active on Bitcoin when Satoshi was working, but before he retired, he disabled these opcodes. So uh, this gentleman, Rusty Russell, has come up with a proposal that these opcodes should be activated again, which is known as, and he has named it as the Great Script Restoration, meaning restoring these opcodes on Bitcoin script. He's created a great he has created something that he calls the Great Restored Script Interpreter. It's script interpreter basically, which supports all of these opcodes that we talked about that have been disabled. Right, so you can create scripts using these opcodes and test them. This obviously won't be for testing purpose. Somebody can use this to test the opcodes that were disabled by Satoshi, the ones that were enumerated by me in the article just a while ago. This script interpreter allows you to create Bitcoin scripts that support those opcodes. These were the four, you can say, new client softwares or updates or changes to services of the existing client software that we had to cover. We're at 8:43. Let's see if we can cover a couple of PRs. Which one? Cool. Bitcoin code. Bitcoin code PR 30666 adds recalculate best header function to recalculate the best header by iterating over the block index, which is automatically triggered when the invalidate block and reconsider block RPC commands are used, or when valid headers in the block index are later found to be invalid during full validation. This fixes an issue where the value was incorrectly set after these events. This PR also marks headers that extend from an invalid block as block failed child, preventing them from being considered as mbest header. So there is this mbest header. Okay, it points to the best header. It points to the best header. So what I mean, if a Bitcoin node sees a header, it validates that header before it actually gets the entire block, right? First, the header is validated. Your peer might share a header with you, which you validate, and if the header is valid, then you ask for the entire block. Now, what could happen is that the block might be invalid. The block might be invalid because it is not in compliance with the consensus rule. In that situation, you trigger the invalidate block. You trigger the invalidate block and reconsider block and reconsider block. In this situation, what will happen is that this function, recalculate best header function, will get triggered, and your header that corresponds to a block that you have invalidated will not be deemed as the best header anymore. Will not be deemed as the best header anymore. So if you had a header that you appended to your chain, and then you ask for the entire block, and the block is invalid, for some reason, in that situation, the header that is corresponding to that block will not be deemed anymore as the best header, meaning it will not be accounted for. And if there are this PR also marks headers that extend from an invalid block as fail. Meaning if there are subsequent headers, if there are headers that are appended further to a header whose block has been invalidated, then even those subsequent headers that have built on top of the header which has an invalid block will not be considered as valid headers. They'll be considered as block failed child. Okay. So this new function has been added. It gets triggered when RPC invalidate block or RPC reconsider block are issued. And what it does is that if there is a header that is being deemed as the best header, but it corresponds to an invalid block, then that header will not be considered as the best header anymore. And if there are any more headers that are appended to that header, even those headers will be abandoned and they'll be considered as block failed child. Uh, let's look at another one. Bitcoin Core PR30239 makes ephemeral dust outputs standard, allowing zero fee transactions with a dust output to appear in the mempool, provided they are simultaneously spent in a transaction package. This change improves the usability of advanced constructs such as connector outputs, keyed and unkeyed P2A anchors, which can benefit the extension of protocols such as LN, ARC, timeout trees, BitVM2, and others. This update builds on existing features such as 1P, 1C relays, truck transactions, and sibling election. We have covered this in detail. Previously, we have covered what ephemeral dust is. We have covered what dust is. We have covered what ARC is, timeout trees are. We have covered what truck transactions are. We have covered what 1P, 1C topology is. We have covered what sibling election is. So basically what happens is now that this PI makes ephemeral dust outputs standard. What are ephemeral dust outputs? They are zero value. They are zero value, zero fee paying outputs that I believe pay to opt-through scripts. If the definition is not very long. Ephemeral anchors are a proposal to allow some transactions to be relayed even if they don't pay any transaction fee, meaning zero fee, provided they're relayed as a part of a package containing a child transaction which pays a fee sufficient for the entire package. The proposal is built on top of the V3 transaction relay proposal, a V3 transaction containing as little as zero fee that has zero value output paying opt-through. Okay, so all three of my assumptions came true. Ephemeral anchors are basically outputs that have zero value, that pay zero fee and pay to an opt-through script, and their only use case is to mitigate pinning. Not the only use case, but an often mentioned use case is that they are used for mitigating pinning attacks. So you attach a child to them, the child bumps the fee of the parent, and you broadcast them as the topology of one parent, one child, and they will be and they will be broadcasted to the mempool as a truck transaction, and they will now be deemed as standard transactions. That's what this PR achieves. Let us look at one Lightning as well. Let's see this. Core Lightning number 7800 adds a new list addresses RPC command that returns a list of all Bitcoin addresses that have been generated by the CLA node. This PR also sets PUTR as the default script type for anchor output spends and for unilateral close chain addresses. So you now have a new RPC list addresses. If you're a Core Lightning user, what does this RPC command do? It does nothing but returns you the list of all the Bitcoin addresses that have been generated by the CLA node. Pretty straightforward. This PR also sets PUTR as the default script type for anchor output, spends, and for unilateral close change addresses, right? We've discussed in detail what anchor outputs are. They're also a mechanism of mitigating pinning attacks in case of unilateral close changes, all right? So PUTR is now the default script type for anchor output spends and for unilateral close change addresses in Core Lightning. That is all that we will be able to cover in this section, as I'm not keeping well. We covered the changes to services in client software, 4 of them, and we covered 2 Bitcoin Core PRs and 1 Lightning PR. That is it from my end. If any of you have anything to share, please feel free to go ahead and do so. Else, we can call it quits for the day.